In this video, I just wanted to review some of the stuff that we went over in Chapter 1. The first thing we did was function composition. So you can read all the white on your own, but what function composition really is using a function as the input of another. So in this example, we have the function f with input x, which is x squared plus x. So what this says is that our function f means that we have some input squared plus an input, okay? In the function g, we have 3 times an input plus 1. So when we compose these two, f of g of x, we're really taking g of x, squaring that, and adding it as well, just like in f of x. So when we do that, we have to FOIL 3x plus 1 to get 9x squared plus 6x plus 1, and then we have the 3x plus 1 left over. If we combine like terms, we get 9x squared plus 9x plus 2. The same thing is true for g of f of x. We're taking the function g with input f of x, so input x squared plus x. So we have 3 times our input plus 1, which is 3x squared plus 3x, and then plus 1 still. The next thing we went over was the parent functions, just in general. So these 6 parent functions I'm expecting you to know. The first is f of x is equal to a constant. If this is the case, we just have a horizontal line shown in red. The second parent function is f of x equals x, which again is shown in here. You are most used to this looking like y equals mx plus b. The next function we have is f of x is equal to x squared, which is the parabola. We know a lot about this. We know how to find the zeros. We know how to find the vertex, which we will go over later. X squared is the parabola. The next f of x is equal to x cubed. Starts low, ends high. F of x is equal to the square root of x. Starts at 0, 0, kind of gradually goes off into the positive direction. And then f of x is equal to the absolute value of x, which are just 2 lines originating at the origin. We can manipulate these graphs in a lot of different ways. We can shift them up and down, we can shift them left and right, and we can invert them across the x-axis or across the y-axis. So first, shifting up and down. So when we have a function g, which is one of the apparent functions above, if we just add a number to that, we just shift the entire graph up. So for example, if we have f of x is equal to x squared plus 4, that is just the parent function x squared shifted up 4 units. So it'll just look kind of like that. If we have the function g of x, which is just one of our parent functions minus some number, we go down that number of units. So for example, again, if we have f of x is equal to x cubed minus 2, our parent function is still going to look the same, it's just shifted down 2 units. So it'll look something like this. We can also shift horizontally. So if we have some function g is equal to some parent function, but we're changing the input, so we're subtracting some number from the input inside, we're going to shift right that number of units. Okay, so for example, if we have f of x is equal to the absolute value of x minus 5, we shift the entire absolute value function over to the right 5 units to look something like this. If we add some number to our input, we're shifting left that number of units. So again, for example, if we have f of x is equal to the square root of x plus 2 inside, we're shifting our entire square root function to the left 2 units. So it'll look something like this. And then we can also reflect them. So if we have a function g of x is equal to the negative parent function, we flip that parent function upside down. So for example, if we have f of x is equal to the negative absolute value of x, we take our parent function absolute value of x and flip it upside down to look something like this. And then we can also shift it across the y-axis by making our input negative. So if we have a function that is equal to a parent function but with a negative input, we flip it left to right. So if we have f of x is equal to the square root of negative x, we have our original square root function, but it's going in the opposite direction. It's like that. We can also stretch and shrink our parent functions. So if we have some function g, which is a multiple of one of our parent functions, it will either stretch or shrink. So there are two kind of different categories. One is when we multiply by a value of c, which is greater than 1. When this happens, we get a vertical stretch. So say we have our parent function x squared. If we multiply that by something greater than 1, for example 3, our graph is going to go up steeper to look something like this. If we multiply by something between 0 and 1, it's going to get a lot wider. So if we multiply by something like 1/2, it's going to look the same, it's just going to look a lot wider. The example in red is called a vertical stretch, because if we were to take both ends of the y-axis and stretch it apart, our parent function would get narrower. If we're multiplying by something between 0 and 1, it's called a vertical shrink, because if we were to take both ends of the y-axis and squish it together, our parent function would be a lot wider. So that's a vertical stretch and a vertical shrink. We can also do a horizontal shrink and a horizontal stretch. So horizontally, we're always dealing with inside of the parentheses or dealing with our input. So if we multiply our input by something greater than 1, we have a horizontal shrink, which will make it steeper. So if you take our parent function f of x is equal to the square root of x, if instead we multiply our input by 3, it's going to be steeper. So it'll look something like this. If instead we multiply something, if we multiply our input by something between 0 and 1, it's going to be a horizontal stretch, which will make it a little bit wider. Like something like that. So a good rule to keep in mind is that if you're dealing with anything outside parentheses, it has to do vertically. And if you're dealing with anything inside parentheses, anything to do with the input, you're dealing with stuff that happens horizontally. And then the last thing we talked about in this chapter were inverses. So the inverse of a function is basically just switching the domain with the range, so switching the input with the output or the x with the y. In order to find the inverse of any function, we swap variables and solve for y. In order to tell that whether or not a function actually has an inverse, it must pass the horizontal line test as well. Alright, so just in general, if we have some graph, we know that it's a function by the vertical line test. So if we draw a vertical line anywhere along this graph, if it only hits the graph once, then we know it's a function. But in order to see if it has an inverse, it has to also pass the horizontal line test. So if you put a horizontal line along the graph and it hits more than once, then its inverse is not a function. In order to actually find an inverse, all we do is swap variables and solve for y. So in this example, does this function have an inverse, and if so, what is it? The first thing we need to do is to determine whether or not it has an inverse. So this function has a parent function of f of x is equal to the square root of x, and it's shifted right 5 because of this, and then it's shifted up 4 because of this plus 4. So it's right 5, up 4. So if we were to graph that, it would look something like this. Now we know it's a function because it would pass the vertical line test. It would also pass the horizontal line test, because this horizontal line would only ever cross the graph once. So now we know it does have an inverse. Now we need to actually find the inverse. In order to do that, again, we swap variables and then solve for y. So we would have x is equal to the square root of y minus 5 plus 4, and we need to get y by itself. Now this line right here also tells you your domain. So this number right here will always be positive or 0. So our domain would be x is greater than or equal to 4, because no number will decrease this constant. Now in order to solve, we'd have to subtract 4 from both sides. In order to undo the square root, we square both sides. And then we have to add 5 to both sides. And then this is our final answer. Now, this is just a quick review. I didn't go into everything super detailed, but this should be a quick reminder of everything we went through in this chapter. We will also go over this more during the review, but if you have any questions, please feel free to email me. Again, I know this is a quick rundown, but it should touch everything that we went over this chapter.